Hello, my name is Emily Ireland, and this is my fifth and final lab for the Physics 1 class at Georgia Tech. And for this Choose Your Own Adventure lab, I chose a falling slinky. Some important background information. The purpose of this lab is to predict the motion of a falling slinky. The result found was that although there are some fluctuations, most likely due to error, the bottom of the slinky remained stationary. The system of this experiment was a slinky, and the surroundings were everything else. And some important fundamental principles to note are Newton's second law, drag force, and gravitational force. Newton's second law is important because of the system's change in momentum to net force applied, and drag force is important because of air resistance as the slinky falls through the air. Some important formulas to note. The F-net formula that says that F-net is equal to the change in momentum over the change in time. The momentum, velocity, and position update formulas, the force of drag formula, the force of gravity formula, and the formula for the force of tension of the slinky. So, this is a screenshot I took from the tracker app showing that I tracked the bottom of the slinky and it shows the motion of the slinky. So, using a previous lab's glow script code, I changed some initial conditions to fit this lab. I changed the ball.m to be 0.204 because that was the predicted mass of the slinky. I also used the tracker information to find the initial position vector, and since the slinky did not originally move, I set the initial velocity to be 0. Through trial and error, I set the proportionality constant to be 102. The first while loop is set for when the bottom of the slinky is still stationary. I found this using the velocity and position update formulas. Because the velocity is 0, the F-net is also 0. Note that this happens while time is less than 3.933. The second while loop occurs after the bottom of the slinky starts moving. This happens while t is less than 7.283. Here, the F-net and velocity are no longer 0 because the bottom of the slinky is moving. This was also found using the velocity and position update formulas. This is the graph I got in Excel when comparing the experimental results from Tracker and the computational results from GlowScript. As you can see, the observed or experimental is in the dark blue, and the modeled or computational model is in the light blue. These do not perfectly align, however, they are pretty close, meaning that the computational model probably well fits what actually happened. So, some possible sources of error for this lab. I could have easily made a mistake using Tracker, as it's easy to mess up finding the exact position through a video. I could have also made some calculation errors. A big source of error could be the trial and error method I used to find the proportionality constant. I could have also made coding errors. And a big source of possible error are outside forces that are not accounted for in the actual experiment. So some discussion questions. Why does the bottom of the slinky remain stationary? This happens because the gravitational force on the slinky and the tension force of the slinky cancel each other out. The gravitational force points downwards, but the tension force points upwards with equal and opposite magnitude. And the second discussion question is, why are the experimental and computational model different? This is most likely because of outside forces that I did not account for in this experimental lab. Anything from wind to imperfect hand movement or a multiple of other things could have made this experiment imperfect. Thank you for listening.